Hi, in this short talk, I'm going to talk about classification of distributed binary labeling problems. This is joint work with Alkida, Sebastian, Juho, Yannic, Dennis, and Jukka. So in this short talk, I would like to convince you of the following sentence, that the distributed complexity of homogeneous binary labeling problems on trees is decidable. We are going to break this sentence down into all of its components and understand them one after the other, starting with distributed complexity. In this talk, we are going to focus on the local model of computation, in which we have a network of n nodes, and each node has a unique identifier. Communication takes place in synchronous rounds. The initial knowledge of each node is only his immediate neighbors. We have unbounded local computation, and our complexity measure is going to be the amount of rounds. Next, we are going to discuss binary labeling problems. So in binary labeling problems, we are given a graph, and we are tasked with labeling its edges either red or blue, such that some radius 1 neighborhood constraints are satisfied. For example, in this graph, a labeling of the edges by red and blue can be, for example, this one. Some examples of such problems include two coloring, perfect matching, and synchronous orientation. Now you might think it odd because two coloring is a problem where we need to label vertices and not edges. I will elaborate on that later. So now, for a more formal definition, as we said, we are going to focus on trees, more specifically on two color trees as input. Although this might seem restrictive and weakens the expressiveness of our framework, I will convince you otherwise in a moment. And a binary labeling problem is a tuple which consists of D, delta, W, and B, where D is the degree of the white nodes, delta is the degree of the black nodes, and W and B are binary strings of length D+1 and delta +1, respectively, that are the white constraint string and the black constraint string, respectively. So here's, for example, a two-color tree. And intuitively, and actually formally as well, the constraints are going to affect the problem as follows. We are going to have that Wi equals 1 if and only if the white nodes are allowed to have exactly I incident edges that are colored red, and similarly for Bi. So let us take some example of such a problem to understand it better. Let us consider the following problem, where the white degree is 4 and the black degree is 2. I know that there are leaves in this graph, but let's ignore them for a moment. So we see from these constraints the following. White nodes need to have at least one red edge, and black nodes need to have exactly one red edge. So for example, the following solution is valid. Again, if we ignore the leaves for a moment. However, this solution is not valid because we have a white node here who does not have any incident red edge. You may see, maybe, that this is basically the simplest orientation problem on graphs of degree 4. And why do I claim that when I have black nodes of degree 2? Well, assume we were actually given just synchronous orientation problem on the graph without the black vertices, and we wanted to solve it. Well, what could the vertices do? Well, actually, they could simulate the black vertices of degree 2, and then solve this binary labeling problem as before. And then after they achieved the solution to the binary labeling problem, they can now find a solution to simplest orientation in the following way. Simply direct red edges to blue edges. So for example, there is going to be an edge directed from this node to this node as this. And now we already obtained a simplest orientation of the white nodes. So we can again get rid of the black nodes. So you see, although allowing the input to be a two-color tree might seem restrictive to our framework, it actually strengthens the expressiveness of the problems we can deal with. And now to tackle the slight issue that I mentioned regarding leaves. Well, we are talking about homogeneous binary labeling problems. By that I mean, well, that nodes that are not of degree D and are white and are not of degree delta and are black, we just don't care about them. And all labelings to their incident edges are valid. And because of that, we can ignore leaves. So for example, in this graph, we don't care about the labelings of the edges adjacent to these nodes. And now for the main part, and it's what I mean by decidable. And here we get to the main theorem of our work. And the main theorem is as follows, that the deterministic complexity in the local model of any homogeneous binary labeling problem has to be one of the following. Either it's O of 1, and not only can it be O of 1, we also show that the only problems which have O of 1 complexity are those solvable in zero communication rounds. From there, we immediately jump to theta of log n with nothing in between. So in particular, this means the theta of log star n disappears, which is very surprising because many natural symmetry breaking problems, such as maximal matching and MIS, are known to have complexity theta of log star n, which means that these problems cannot be expressed using only two labels. From theta log n, we immediately jump to theta of n. And as you can see, we can represent two coloring using our framework. And we have the unsolvable problems. Not only that, but given the description of a homogeneous binary labeling problem, we can very easily find out its complexity and what is the optimal algorithm that solves it. This is depicted in the following table. We have the following legend here, where this dot means it can be either 0 or 1. And as I said, we have the unsolvable problems, which, as you can see, is really easy to check whether a given binary labeling problem has the following pattern or not, to decide if it's unsolvable. We also have the problem solvable in constant time. And again, it is very easy to check whether a problem has one of these patterns. Then we have the global patterns, the global problems, and the same holds. And all of the other problems have complexity log n. So we also, in our work, start exploring the randomized classification of homogeneous binary labeling problems. And what happens there as well, that deterministic log n splits into theta of log n and into theta of n. Examples include simplest orientation for theta log n and perfect matching for theta log n. Although it is not a complete classification, and open cases do remain. To sum up, we know now that the deterministic complexity of any homogeneous binary labeling problem in the local model is either O of 1, log n, or it is unsolvable. Furthermore, this is the first step towards automatizing algorithm design for distributed computing. And for open problems, we leave it as completing the randomized classification and considering problems with more than 2 labels. For example, when one considers 3 labels, already more complexities appear, such as log star n. Thank you.